Our goals of this lesson are to determine period, amplitude, and phase shift of cosine, sine, and tangent, which will be in the next unit, but the same ideas will apply. And our second goal is to graph, state, and perform transformations of sine, cosine, and tangent. Again, tangent will be the next unit, but the same ideas will apply to this function. So first, we're going to define a sinusoid. A sinusoid is f of x equals a sine b of x minus h plus k, where a, b, and h and k are constants, and a and b cannot equal 0. This same thing goes for cosine. So sine and cosine are both sinusoids. Now, the period of a sinusoid is 2 pi over b. Graphically, this looks like the length of one full cycle of the wave. So we think of sine being kind of like this. So that is one full length of the wave. The length of that is going to be our period. So we know a function is periodic if there is a positive number such that f of t plus c equals f of t. This smallest number, c, is called the period of the function. Again, the period is one complete cycle length. So the periods of sine and cosine, when just without our transformations, are 2 pi, and then tangent will be pi. The period of sine and cosine is the same since one is a horizontal translation of the other. Also, we'll have frequency. Frequency is the number of complete cycles that a wave will make in a unit interval. So if it makes within a unit, it can be more than one period long. We'll talk about the frequency. So right now we're going to look at period. So for period, we want to list the period of each of these. First, we have y equals negative 2 cosine of x over 3. We have to remember that period is 2 pi over the absolute value of b. So here, our period will be 2 pi over the absolute value of b, which will be 1/3 in this case. It would be 1/3 times x, our b values on the inside. And this will simplify to 6 pi. We multiply top and bottom by 3. So the period of this function here is 6 pi. Let's look at the next one. Y equals cosine of negative 4x. Again, our period is 2 pi over b, the absolute value of b. So we'll have 2 pi over the absolute value of our b, which is negative 4. So then we'll have 2 over 4, which is pi over 2. So the period of this function is pi over 2. Now, it's important to remember that f of cx is a horizontal shrink, and f of x over c is a horizontal stretch. So here, we have more of an x over c, and that gives us a horizontal stretch. So where the period you would think would be 2 pi, this b value stretches it out so that our period is now 6 pi. Looking at this one is this other form, f of cx. So where normally cosine of x has a period of 2 pi, this b value here is a horizontal shrink, causing the period to be now pi over 2. So now let's talk about amplitude. The amplitude of a sinusoid is the absolute value of a. Graphically, this is the height of the graph. So a horizontal stretch or shrink is going to be our period, and a vertical stretch or shrink is going to affect our amplitude. So what is the amplitude of these functions here? So for the first one, our amplitude is going to be 1. Our amplitude is the A value. See, we're used to seeing this as y equals A sine x. So we can see our A here is 1, so we know our amplitude is 1. So we want to sketch this. We know our period is 2 pi, because that'll be 2 pi over b, which is 1. And we can sketch this. Sine, our value is going to be 0 here. Then at pi over 2, the sine of pi over 2 is going to be 1. Then we'll go down to pi, 3 pi over 2, negative 1, and 2 pi. And we can connect these points. And this will be a sketch of our sine function. Now, what happens when we end up with an amplitude of 1 over 4? So here, our amplitude is 1/4. Since our b value is 1, our period is still 2 pi. So now our amplitude, or the max height that the sine function will reach, is 1/4. And again, it's still over a period of 2 pi, so it looks a little more squashed vertically. Now, let's try one more. So this one has an amplitude of 2, but now we have this negative in front, so we need to reflect over x. So we'll start here. Normally we would go up to 2, down to pi, down to negative 2, and up to here. But since we're reflecting over x, you need to, this point stays the same, reflect this point stays the same, reflect this point, and this point will stay the same. So we'll trace our function, and now we see our graph is vertically stretched. So now, let's see what happens when we try and move our functions left and right. The f of x plus c results in a horizontal shift left c units when c is greater than 0. For sinusoids, we're going to call these phase shifts. So a phase shift of a sinusoid is going to be our h value. The vertical shift is going to be k, this part here is k units up or down. So now, we want to take these examples, and we want to state the amplitude, period, phase shift, and vertical shift of all of these functions. So, let's see for the first one. Our amplitude. Our amplitude is our a value. So our a value here is -5. So we need the absolute value of -5. So our amplitude is going to be 5. Our period is going to be 2 pi over b. So for this one, we might want to factor out that 3 to see what our period is. So to factor out a 3, we're going to have y equals -5 cosine of 3 times, so now I'm going to factor out this 3, x plus pi over 18 plus 0.5. Now, it's pi over 18 because if you distribute this 3 back in, you'll get 3x plus pi over 6. So now we can look at our period. So our period is 2 pi over the absolute value of b. So here we can see our b value is going to be 3. So we'll have 2 pi over 3. Now, let's look at a phase shift. Our phase shift is going to be our h value, which is right here. This is our h value. So, looking at this, our phase shift is going to be going to the left pi over 18. Because this here is positive, we got to do the opposite. Now we need our vertical shift and check for any reflections. So we've taken care of everything inside the parentheses. Our reflection is still attached to the function, so we need to reflect over the x-axis. And then lastly, we need to go up 0.5 units. So that is everything for this problem. And now let's see how phase shifts kind of tie into the period for sine and cosine. So we need to write sine or cosine as a phase shift of the other. So sine of x is going to be cosine of x minus pi over 2. And cosine of x will be sine of x plus pi over 2. Now, reason being is because our sine and cosine functions are horizontal shifts of each other. So, if we look at sine of x, we can graph sine of x on our calculator. And we'll change our window, so we'll use 0 to 2 pi. Actually, my calculator's in degrees, so we got to change the mode. Mode will go down to radian. And change the window a little bit, 0 to 2 pi. So this will get our full wave. And we can scale by, let's say, pi over 2. Y minimum, -1, y max, 1. Okay, so here's the graph of our sine function. Now over top of it, I'd like to graph cosine. Now, watch what happens when I change cosine and shift it pi over 2 units. So this is our sine function. Then cosine plus pi over 2. Doesn't quite work. So now, this is why we can see that our sine was actually our cosine minus pi over 2. And let's see what happens here. So there's our sine function. Here's our cosine function. It traces right over it. So this is how we can see why sine is cosine minus pi over 2. And then our cosine would be sine plus pi over 2. Alright, let's move on. Here are a few problems that you can try. Now, some things to keep in mind while you're trying these. You want to make sure you label your axes. The period is very important. So the period may change, your axes may change. Now the amplitude is also need to be measured. Your amplitude will be on the y. So you want to start with your parent function. So for these, your parent functions are going to be sine and cosine. Then you're going to apply your transformations. Keep in mind period, amplitude, phase shifts, and then reflections. These ones don't move up and down vertically at all, but you want to keep those in mind. So you can try these, and I'll check them tomorrow in class. All right, that's it.